Hi, people. We're going to start a new unit, and this unit is about one main topic and a couple of offshoots of that. It's about energy. And the other ones work and power. There's a comma. Energy, work, and power. Okay? There are lots of kinds of energy, forms of energy. What I'd like you to do for tomorrow is list as many as you can. Different kinds of energy you've heard of or are aware of. Because a lot of this unit is about energy changing forms and transitioning or transferring or changing from one kind into another. Okay? So I'll give you two. We're going to concentrate in the very immediate future on two kinds of energy. Well, sorry, let me start with one kind of energy. Mechanical energy. Now, mechanical energy for us is about, whoops, I'll put this in the middle. So again, you can make a little list of that. Mechanical energy for us has three main components. Now, of those three, we're going to deal with two of them right away. The third one will wait for a little while. All right, and those two main components, one's called kinetic energy. And the other is called potential energy. Right? Now, kinetic energy is about this. Kinetic usually refers to motion. So we call this energy of motion. And potential energy, sometimes people call it stored energy, which isn't my favorite way to do it, but I'm going to call it this. I'm going to call it energy of position. Okay? Now, kinetic energy works like this. Well, you kind of have to think about what kind of object would have a lot of kinetic energy. What kind of object would have a lot of energy associated with its motion? Well, I'll say this. The more massive things are, the more kinetic energy they could possibly have. That's one. And two is faster objects can tend to have more kinetic energy, which says that kinetic energy depends both on mass and, well, velocity. All right, so it starts to sound a little bit like momentum, but momentum's about mass and velocity also. Now, kinetic energy isn't just m times v, because that's momentum. It's actually 1/2 mv squared. Why? I don't have a great answer for that. Okay, the 1/2 especially, I don't have a great answer for. So there's that. Okay, now. So this just says, you know, if you want to know something's kinetic energy, multiply its mass by the square of its velocity and multiply that by 1/2. And there you go. Okay? Now, this potential energy, energy of position, there are really two kinds of that, but we're going to talk about one that we call gravitational potential energy. All right? So what kinds of things have more gravitational potential energy? Well, I'll say this. oops, one still. Just like kinetic energy, more mass equals more PE. All right, and the other thing is this. It doesn't have anything to do with how fast things are moving, right? But it does have to do with where things are. And since it's gravitational stuff, it has to do with how high up things are. Whoops, that's supposed to say higher. And so this one goes like this. We say that PE, with a little subscript G there for gravitational, well, deals with M, and H, well, and G. Because, right, it's about gravitational potential energy. So we use acceleration due to gravity. Or, what you've heard me say before, this is actually gravitational field strength. Little g is the same thing. Gravitational field strength and or gravitational acceleration. Okay? All right, so here's two formulas that you need to know. They're in the reference table. But you need to be able to solve problems with those. Now, a couple of qualifiers. Let's say this. Well, objects can have one kind of mechanical energy, or comma, or both, or neither. You run into this a lot, or I run into it every year. People say something like, if it's moving, then it can't have PE also. That's not true. All right, so, and really, to tell you the truth, mechanical energy, by definition, mechanical energy is the sum of those two energies. And really a third kind, but again, like I said, we'll deal with that third kind coming up in a couple more weeks. All right, so here's another thing that you have, you should be able to do based on how fast an object's moving and its mass and where that object is. You should be able to find its total mechanical energy. Okay? A nice little note here about this, about gravitational potential energy, is that it's always necessary to define slash well, we'll just say define gravitational potential energy with, or in comparison, I should say. How about that? In comparison to some place, because when we say h is height. Well, you know, how high up is this tennis ball that I'm holding in my hand? Well, it depends. Are we talking about above the floor, or above the Earth's surface, or above this tabletop? So we have to define PE in comparison to some height that we call 0. And I'll put a little asterisk. You can pick 0 height. To make questions easier. Now you can't always do that, because if I say, well, what's the tennis ball's gravitational potential energy compared to the floor, or with respect to the floor? Well, I've defined for you where 0 height is. But if I just said, hey, what's this bowling ball's potential energy, gravitational potential energy, A, that's not a great question. B, you could say, well, if I call the height that it's at right now zero height, then its gravitational potential energy is zero. Easy, right? I don't even care what its mass is. So there will be times where you get to pick the zero height. All right? Keep your eyes peeled for those. Let's see. Oh, another big thing about these. I'll go back up to the top for this one. Energies of all and every kind are all scalars. Okay? There's no such thing as the direction of an energy. All right? So an object moving this way and an object moving that way can have the same kinetic energy. We saw in a little quiz that they cannot have the same momentum. Because momentum does include direction, but kinetic energy does not. Okay? And kind of like we said with momentum, it's certainly possible for objects of different masses to have the same kinetic energy, right? Their velocities would have to be different also. Okay? The units for energy, well, let me see. If we take the 1/2 mv squared, well, the 1/2 doesn't have units. Mass is measured in kilograms. V is measured in meters per second, but it's V squared, so it's meters squared per second squared. Well, those are the units of energy, the kilogram meter squared per second squared. All right? That's one way to do it. People very rarely talk about those units for energy. What you could do is do this, a kilogram meter per second squared times a meter. Now this, you might recognize as like M times A. And M times A is force. So this is actually a Newton, and then times that meter. So sometimes people do talk about energy in Newton meters, but then we call that a joule. So the standard unit of energy is the joule. I know we've seen capital J recently as impulse. That's not what we mean here. Impulse, capital J, is a variable, a quantity. This capital J in our square brackets means those are the units that energy is measured in joules. That works for kinetic energy. Now let's look for gravitational potential energy. If we say mgh, well, that's m in kilograms, g in meters per second squared, h in meters. Yep, same thing. All right, notice mg, that's a force, right? So here's a force. Again, there's a Newton times this meter. A Newton meter, same thing, is a joule. All right, so every kind of energy that we deal with will be measured in joules. All right, but remember, that does mean that masses have to be in kilograms, h's have to be in meters, speeds have to be in meters per second. Okay? I'll have a couple of example problems for you to work through soon, and having this stuff in mind will get you ready for a lab pretty soon. Okay? What else? What else? What else? I think that'll do it. Adios, amigos.